This is a video for MEI Core Pure Mathematics, Calculus 2 Inverse Trig Functions, 2.2 Differentiating arctan x. There are two main ways of writing the inverse tangent function. Both arctan x and tan to the minus 1 of x are commonly used. But it's important that you remember that tan to the minus 1 of x refers to the inverse tangent and not the reciprocal 1 over tan x. We will use arctan x throughout these presentations. Here's a graph of arctan x. You'll see that the range for arctan is minus pi by 2 to pi by 2. The blue line is the tangent at this point here, and you can see that the gradient of that tangent is positive. And by looking at the curve, you can see that actually the gradient of arctan x is always positive. And we can write that dy by dx is greater than or equal to 0. So how do we differentiate arctan x? Well, if y is arctan x, then we can write that tan y must be equal to x. We can differentiate this implicitly, giving me that sec squared y dy by dx is equal to 1. And then rearranging that to give me an expression for dy by dx, I'm going to get that dy by dx is 1 over sec squared y. Now we can rewrite sec squared in terms of tan squared, and that means we can rewrite this expression as 1 over 1 plus tan squared y. From up here, we can see that tan y is equal to x, and so I can now substitute back to get that this is 1 over 1 plus x squared. And so I can write that my derivative, d by dx, of arctan x is equal to 1 over 1 plus x squared. There's that working tidied up. So this is where we switch the function round, the implicit differentiation, bit of algebra to get back to an expression in terms of x, and our final result. So back to our graph of arctan x. It's slightly different because I've drawn the tangent at x equals 0, and looking at the algebra up here, when x equals 0, dy by dx is equal to 1. And the blue line actually has a gradient of 1. Looking above 0, the line gets shallower, and below 0, it also gets shallower. And this means that the gradient of arctan x is always less than or equal to 1. And so, in fact, our gradient must lie between 0 and 1. Okay, let's look at a more general derivative. As before, we're going to rewrite this as tan y is equal to x over a this time. And differentiating implicitly, I'm going to get sec squared y dy by dx is equal to 1 over a. Rearranging that to get an expression for dy by dx, we get that that is 1 over a sec squared y, and as before I can rewrite sec squared as 1 plus tan squared, so I get 1 over a times 1 plus tan squared y. This time the substitution is that tan y is x over a, So putting that in, I'm going to get 1 over a times 1 plus x over a, and that bit is squared. So there's a little bit more work to do to tidy that up. If we look at the bottom here, do a bit of work in the brackets to give me a squared plus x squared all over a squared. And the a outside here will cancel off with one of the a's on the bottom here to give me finally a over a squared plus x squared. So our derivative, d by dx, of arctan x over a is equal to a over a squared plus x squared. Again, tied it up for you. The function rearrangement and the implicit differentiation. A little bit more work in the algebra to get down to an expression in terms of x, and our final result. So in summary, if we differentiate arctan x, we get 1 over 1 plus x squared. And if we differentiate arctan x over a, we get a over a squared plus x squared. And this latter result we will see is quite useful when we look at integration in a later video. The next in the sequence is 2.3 integrating using arcsine x.